Okay, it's just after 11 o'clock. Time to get started. Thanks everyone for joining us today for our webinar. This is all about materials. There we go. I wanted to keep this introduction brief, so I used acronyms. I'm Dan. I'm a Michigan Tech grad, and I'm SolidWorks certified as a post-sales application engineer here. My role at Unitech is focused on our current customers. I'm here to make sure that folks get the most out of their investment, and sometimes that means helping our service technicians diagnose print problems. Sometimes it's working with CAD data to improve printability in specific parts. Some of you may know me from the Advanced Insight training class that I teach here at our headquarters in Pleasant Ridge, but it's also my job to understand materials and how to use them effectively. And so that's the subject of today's webinar. Now, full disclosure, you'll notice that the letters PhD are not in this list of acronyms. I'm a mechanical engineering technologist, not an organic chemist. So my knowledge of the subject is very much a work in progress. So my goal here today is to share some of that knowledge with you to the best of my ability. And that means being very deliberate on how I present this information and to whom it is intended. So who's my target audience today? Well, the owners and operators of some of the big Stratasys equipment, namely the production systems, the F900 or Fortis 900 MC, the Fortis 450, 380, the older 400s, 360s, maybe Titans, etc., and the F370. Basically, all of the FDM equipment that runs multiple materials. And I'm also speaking to owners and operators of ABS-only machines, like these down in the corner, who might be considering an upgrade or who are looking for ways to do more with those machines than they currently are. Don't get me wrong, there's plenty to glean here for everyone. Just know that I will be assuming here a pretty high level of familiarity with the equipment. I won't be spending too much time on basics. All right. Now, my plan is to briefly discuss each of the FDM materials that Stratasys offers in each of three categories. Standard, engineering, performance, which those correspond to material upgrade packages that are available for the Fortis production printers. For each of those materials, I'll explain a little bit about its chemistry, what to expect when printing with it, and what application is best suited to that material. And I'll try especially to identify applications and uses that you might not have thought of already and that you might not already be using it for. Now, in the interest of time, I hope you don't mind that this won't be a sales presentation. I'm not trying to sell you a machine or an upgrade or get you to buy materials. If you do, that is great, but I want to make sure that you're making an informed decision. So I also won't, I want to make sure that you're getting the most out of your investment, as I mentioned earlier. I won't be cluttering up the screen with a lot of facts and figures. I will show you where to get those if you will want them. I'll do that in a minute. But I'm also going to try to keep the technical jargon and terminology to a minimum, or at least avoid using it without first defining those terms. I'm going to try to avoid overstating and overpromising. I want you to be equipped to make a good decision, and that means not overpromising. As I mentioned before, there's a chat over on the right-hand side and a Q&A window. It is very important to me that these webinars be differentiated from our static publications like blogs and videos. I mean, you're here live and in person. I'm here live and in person. Let's make this a little more of a conversation. Now, in the interest of everybody's eardrums, I'm going to keep everyone muted during the bulk of this. I'm going to mute everyone at the end during questions and answers. But in the meantime, head over to the right side of your screen. You should see a chat and a Q&A box. If you have a question as we go, toss it in there, and I'm going to do my best to address it as we go. I'll stop after each section and take a look through those Q&As and see if there's anything that I can address at that point. And as I mentioned, at the very end, we'll have a time dedicated for questions and answers. There is a lot here, and I'm going to go pretty quick, but hopefully we can keep this under 45 minutes. Oh, I should also mention that if I don't catch your question right away, it's a little hard to juggle the screens around. So I have somebody else on the side who's also flagging questions. So, all right, let's get started with standard materials. Polylactic acid, all right, better known as PLA, also known as polylactide or poly-2-hydroxypropanoic acid. It's sourced from plant starches and biodegradable. That doesn't mean that you can just throw it on the ground. It needs to be decomposed in a compost pile. But so chemically, this is basically long chains of that lactic acid molecule over there, all tangled together. And just to get some terminology out of the way, that tangledness of those molecular chains is what is meant by the term amorphous when you see that. And since lactic acid is an ester, then we call this material a polyester. And since heat allows it to become moldable, or in other words, to plasticize, it's categorized as a thermoplastic. I should probably mention here that FDM, which stands for Fused Deposition Modeling, that was patented and trademarked about 30 years ago by Scott Crump, who then founded Stratasys. And I should mention that the first commercial FDM 3D printers used ABS, as does every Stratasys machine today. I'll talk about ABS next, but those of you who already have FDM machines are probably wondering why on earth I'm talking about PLA. Well, partly it's because the F123 series can run PLA, which is a first for Stratasys. But I'm mentioning it because, frankly, I think that PLA is the most important material for 3D printing, full stop. I mean, it's not the best, mind you, but I think it's the most important. Because without PLA, I think that consumer-level printers would not be marketable. And 3D printing would not have had the media attention that it has had. And at this point, many of us would still be unaware that 3D printing is even a thing. And the reason for that is that PLA has a really nice blend of properties. The glass transition temperature, that's basically corresponds to how hot it can print. It's quite low. It's a little more than half that of ABS. So that means that it prints cooler. And because it prints cooler, that means that the nozzle is less likely to cause severe burns. It has a low coefficient of thermal expansion, and that pertains to how much a material expands and contracts as it's heated and cooled. So because of that low CTE, it moves less when it's heated. And again, since it prints cooler, there is less heat to move it in the first place. So I think that allowed printers, PLA printers, to have an open frame, which in turn allows them to be built much cheaper, and I should note, without violating Stratasys patents. And PLA happens to be stiff and very strong. Surprisingly, it's actually 40% stronger than ABS. So it's really not a bad choice for structural elements in low-stress applications like, well, for example, 3D printers. And I really think that is what enabled the wrap movement. And that itself was a huge boon to the maker community in general, and that all has helped to bring 3D printers into the limelight. So I'm really glad that Stratasys has embraced PLA in the F123 series of printers. Anyway, in practice, PLA is really easy to use if you understand its limitations. One of which is the lack of a great support material. Because of those magic combinations of properties, it's hard to find another material that's close enough to use as a support material. And that's why most PLA printers on the market have a single nozzle. And so they build support structures out of PLA. On an F123 series machine, you will need to swap the print heads in order to run PLA. I took it apart and I checked. The model tip is a little different. And you'll actually replace the support tip with a cooling fan. And that process on the F-Series only takes about 2 minutes. And the really nice thing here is, since there's just one tip, there is no need to calibrate that machine. You load the material, which itself takes about 30 seconds, and go. Before every print, no matter what material you use, the tip will go back, touch the tray, home itself, and that's all that's required. And that's part of every single print. So without that second material, there's no toggling of heads to go back and forth between the support tip and model tip every 2 layers. There's also no purge block required, which is normally required for ABS and other materials on the F-Series. That all translates to it building much, much faster than ABS, up to twice as fast for big prints. Now, if you have an F123 series printer, like an F370, for example, you should definitely be using PLA for quick and dirty proofs of concepts, like, for example, validating hole placements. Imagine a very large plate where the most important element is the hold down hole pattern. Maybe just build that much, cancel the build, yank it out, test it, and then print the finished part out of another material. Use it for clearance verification. Maybe build a complex assembly, but just the outside shell with a sparse infill. Shove that into the position, make sure it doesn't bump into anything. So that kind of stuff. It really works great for anything that doesn't need to be solid, because that's the default build style in GrabCAD. Also, PLA comes in 11 colors, and most of those are actually translucent. The PLA is naturally translucent after all. And so that means it's the only FDM option for translucent parts, at least in most colors. As we'll get into later, there are a couple of other translucent options for you. And finally, if you have the skill and knowledge to design parts that don't require supports, that's the acronym Design for Additive Manufacturing, or DFAM. Well, you can use PLA for pretty much any low heat application where the part does not need to bend, because it's pretty stiff, and when it bends, when it deforms, it usually breaks. It's strong, in other words, but brittle. So parts like spacers, sleeves, maybe grips and handles, that's the thing. You can build those all day long out of PLA. And if you have an F370 and you are familiar with Insight, you know how to use it, you can actually make fully dense PLA parts. And the nice thing about fully dense PLA is that those parts are a good candidate for annealing. Annealing basically means elevating the temperature in a precisely controlled oven somewhere close to its glass transition temperature. That's TG, for a number of hours, 2, 3, 4, 5, 6 hours, depending on the temperature. And once you do that, you elevate the mechanical properties by 20 to 30%. The heat deflection temperature increases too. So overall, PLA is really a pretty versatile material. That's why I spent so much time on it. All right. Next up is ABS. Now, I'll try not to spend long here, since it's what you're all used to, presumably. Acrylonitrile, butadiene, and styrene are those 3 chemical monomers over in the corner. And those make up this so-called amorphous terpolymer. Basically, the way that the chemistry works is that the styrene and the acrylonitrile molecules stick together. And those, we'll call them chunks, they're all connected by long chains of butadiene rubber. So the result, as you are well aware, is a shiny, opaque material that's easily pigmented, It's relatively ductile, and so it'll bend before it breaks. Now, unlike PLA, since we just discussed it, ABS prints with a separate support material. You're all familiar with SR30, maybe SR20 if you have an older dimension machine, but you should be aware of SR35. That's also called QSR on the F123 series. And it's easier to remove by hand, it dissolves faster in the tank, and it's the same price as SR30. So maybe give that a try. Now, ABS, having been around the longest, it has the most finely dialed in parameters. I mean, think about it, 30 years of trial and error, it's pretty well dialed in. So it is extremely reliable. That's why you're all using it. Bear in mind that you'll always get stronger parts, though, with thicker layers. This is something I always cover in my Insight class. Thicker layered parts will also warp less, so your parts are less likely to fail. Now, that all has to do with thermal mass and basically how much internal stress you introduce into your part as you're printing. I go into a little more depth in my class, but anyway, that fact, thicker layers, stronger parts, wider tool paths, stronger parts, that's true of every material that I'm aware of. But I'm mentioning it here early on because, well, frankly, not every machine can run other materials than ABS. And so if you've been running ABS, maybe running into problems at 5 thou or 7 thousandths of an inch, I want to explain that so that you can get the most out of your machine. So as far as applications go, historically, ABS has been the go-to material for prototypes. It's probably what most of you are using it for, especially prototypes with, call it, low fatigue requirements, so where things aren't bending and over again. But there are a lot more uses for it out on the shop floor than most of our customers realize. Some examples, ABS parts can be basically stand-in parts for actual parts. So if you, for example, pause a sparse infill part mid-build and pour in lead shot or sand or pea gravel, you can build a part of accurate size and shape and weight, and then you can use that part to do things like teach robot positions with full kinematic accuracy. And you can do all that before you have actual steel parts in hand. Or you can use it to validate machining operations. You know, if you're testing a machining operation on an aluminum part, substitute plastic instead. It's probably okay if the cutter runs into your part, or go take it one step further and 3D print the cutter. You can even design in a shear point so that it cracks off. That way you don't risk damage to your parts, and you don't risk damage to your equipment. Now, it's worth mentioning that if you're not using all of the ABS colors that are available for your machine, I really wish you would. It's super helpful. It makes it really easy to visualize assembly stack-ups. You know, you're holding something up in front of a classroom. Everything's a different color corresponding to you know, maybe a sheet they have. Really helps for education and training. Also, if you do plan to finish parts, it's a good idea to build with a material that's very close in color to your final end color. As far as colors go, Stratasys sells ABS M30, which is for the Fortis machines, in ivory, white, black, dark gray, red, and blue. So that's for the big production machines. And then ABS Plus P430 for small machines. It includes green, orange, and yellow. Now, on the subject of finishing, ABS can be smoothed with solvents like acetone or MEK. So the way that works is if you expose the parts to acetone vapor or a light mist from a spray bottle, that's what I do, the material will partially dissolve, and that'll fill in some of those crevices, and it'll help smooth the surface out. You can use that same technique and over again, you know, a few iterations to make the part watertight. So it's important, though, that you be careful with those chemicals. A little bit goes a long way. You can cause some deformation of your parts if you use too much, and those chemicals are nasty for you and for the environment. So Now you can also use epoxies and other coatings to seal parts, or you may not have thought of this one, you can use metal. Vacuum metallized ABS, those parts look really awesome. Here's a little example of a mouse, but electroplating is also an option. And if you haven't thought about using building sacrificial tooling, you can actually burn out ABS. You print the pattern, burn them out, used for investment casting. But you could also build parts out of the actual support material. It's as easy as just ticking a check mark in Insight. And then you have a part made out of support material that you can wrap that in a composite material, coat it with rubber, or electroplate it, and then you just simply dissolve the core away. All right, now ABS is available in some specialized blends. And in case you're not aware of them, here are some highlights. So ABS-I is translucent. It's available in 3 colors. You can see those on your screen, clear red and yellow. Unfortunately, they're currently only available for the Fortis 400 and 900 machines. That ABS-I is not to be confused with ABS-M30I, which is the certified ABS. It's certified for biocompatibility. So this is great for food packaging, prototypes, and basically anything that needs to be in contact with the body, as long as they've been sterilized. And then there's ABS ESD7. Now, most thermoplastics are actually excellent insulators, so that means they'll hold a static charge. Just think about rubbing a balloon on your head. Well, ESD7 has a higher carbon content than standard ABS, standard black ABS, and that increases its electrical conductivity. Actually, that 7 in the name refers to the target resistivity, 10 to the 7th ohms, plus or minus 10 to the 2nd. Anyway, this is really great material for use in assembly and testing fixtures for electronics, since it'll keep that static from building up, keep it from discharging onto your sensitive electrical components. All right, and last for the standard materials is ASA. Now, this is basically identical to ABS, and so I'm just emphasizing the differences here. Chemically, the only difference is that the rubber monomer, butadiene, is replaced here with acrylate, and that material is UV resistant. So ASA doesn't break down in UV light like ABS does. So you can basically use ASA for anything you'd normally use ABS for, plus outdoor applications. Now, mechanically, it's about the same as ABS. If anything, it's slightly stronger, but that may not be statistically significant. Now, ABS has part of its properties is that it's able to bridge gaps a little bit better, and so that means that when you're building with a low density infill using ASA, by default, those air gaps between rasters will be wider. In other words, there's less material inside your part, more air, and that's just a byproduct to how well ASA is able to bridge gaps. Also, ASA has a really nice matte surface finish, unlike ABS, which is glossy, and that helps to hide layer lines. So that means you can often get away with thicker and stronger layers, but I really think that ASA is the choice for anytime aesthetics is important. Also, it's available in 10 colors, the same 10 colors as ABS, but they're slightly different hues. And there's also a light gray option. But that does mean that between ABS and ASA, you have all the materials. You've got 21 material color choices to choose from. Now, one thing I maybe should have mentioned on the ABS slide, but I'll mention here, is that if you do run colored materials, you should be sure to run the machine through an extra purge cycle, or a few of them, when you switch back to white or ivory. Especially the blue and red pigments, they tend to stick around and bleed into those lighter colors. If you have a production machine, like a Fortis 380 or 450, you might consider even keeping a separate tip just for those colors. Another option is you can load black first, which seems to do a better job of clearing out the nozzle before you load that white or ivory. So at this point, I want to double check and see if there are any questions here that I can address. Looks like nothing so far. All right, we'll move on. Engineering materials. So now we get into the nylons. So chemically, these are referred to as polyamides. Basically, they are long chains of that there long molecule. Amide refers to the type of chemical bond that connects those. And just in case you're wondering, that number that shows up after the nylon, 6 or 12 or 6,6, that refers to the number of carbon atoms in that base molecule. So the one on screen there, each one of those vertices is a carbon atom. So there's 12 there, 6 in the carbon 6, or nylon 6, excuse me. Now, nylons are semi-crystalline, and that means, unlike amorphous, it means that their molecules can arrange themselves into basically a strong geometric pattern. And that is actually what allows nylon 6, which was the original patented nylon, which was used in nylon stockings. That's what allows that to still be so strong even when it's pulled into extremely fine threads for textiles. Anyway, for 3D printing, all nylons use soluble support, SR110. Nylon 12, it builds with layer heights of 5/1000 to 13/1000 of an inch. If you're using nylon 6, it won't build at 7 thou. And currently, nylon 6 is also only available on the Fortis 900, but we are told that it will be available on the 450 pretty soon. Nylon is a pretty viscous material when it's heated, so the machine needs to apply a lot of pressure to the filament in order to print reliably with it. That makes it hard to start and stop extruding. So the model tip is prone to drooling, where a little bit will kind of ooze out, and that drool can knock thin parts over, tall parts over, and it can affect the surface finish of your parts, and it can cause some other problems too. So for that reason, I would suggest, although it's not mandatory, I would suggest using a sacrificial tower. Tick that box in the options in GrabCAD Print or in Control Center in the options menu. So basically with that sacrificial tower, it'll help prime the tip by extruding immediately before it gets to the part. It's sort of an intermediate step between the purge bucket, purge position, and the actual part, and it'll help to catch that drool. Nylon 12, all nylons, are very hygroscopic, and that means that they absorb moisture from the air, and that really, really hurts printability. So it is very important, especially for nylons, and as we start getting into more of the high performance materials, it's very important to keep those materials dry. Same goes for the support materials, SR100, SR110, all of the Ultem supports. Keep those canisters sealed when they're not in the machine. And when they are in the machine, if you're familiar with the Fortis machines, there's a little door covering up the thumb wheel you use to advance the filament to get it into the machine. And that door has a rubber gasket on it. Pull out the middle of that rubber gasket, close that door while the material is loaded. It'll help keep moisture out. It just prolongs the shelf life of your nylon. Anyway, the other thing about that hygroscopic nature, so we're basically printing the material in its dry state, and after it's printed, it needs to be conditioned, as it's called, or basically rehydrated in order to get the full properties that you're promised. So be sure that you soak nylon parts in the soluble support tank for at least 4 hours. And you know what, actually, I've mentioned it a couple of times here, and I meant early on to show you where to go to find these material properties. I mentioned I'm not going to blow you over with facts and figures. So if you wanted to follow along, you can go to, ooh, the screen is a little bit weird. All right, so I'm not sure what's going on with my screen here. Let me copy and paste it. All right, we're heading to www.fisherunitech.com. So I recently switched back to Firefox, and I see that it's not behaving very well for me today. Okay, I'm just going to walk you through it by memory. You're going to head to www.fisherunitech.com, click on the hardware link at the top, and then pull down to material properties at the bottom, and that'll bring you to a page with 2 buttons, one of which is for MSDS, the Material Safety Data Sheets, and the other is for spec sheets. And that's what I'm looking at, those are the properties that I'm referring to, if you would like to follow along or print any of those out. All right, back to the presentation. Sorry about that. Right, so for nylon 6, I mentioned that nylon is considered semi-crystalline, but in practice, when you actually 3D print with it, it behaves more like an amorphous polymer. So it has a pretty wide softening curve, and really both nylons have quite a low working temperature, even less than ABS as far as the heat deflection temperature, the temperature that it takes to deform a part while it's under load. But nylons are annealable, and Stratasys does have documentation on how to do that, specifically for nylon. And by annealing the part, again, that's the post-heat treatment process, you can raise the heat deflection temperature of nylons to about the same as ABS. Now, that also increases the strength and the isotropic nature of nylons. So the compressive strength for nylon is almost the same. It's almost as high as polycarbonate, which I will get to next. I had actually meant to start with polycarbonate. But it's softer, so it would be even a better fit for part contact applications like fixtures and nests. And it also machines quite well if you need better accuracy or surface finish than the FDM printer can provide. Also, since nylon is very fatigue resistant, it's great for end-use prototype parts that need to flex like over and over. So things like snap features, living hinges, dust shields, especially for nylon 12, all great applications for nylon. Now, nylon 6 would be great in those applications too, but bear in mind that it is 70% stiffer. All nylons are especially chemical resistant. It's just part of that amide bonding. And so they do really well with particularly problematic chemicals like gasoline, motor oils, grease, all the sorts of things that you'd expect to get on an automotive part, but which would normally eat up ABS and polycarbonate. Now, the last thing I want to mention is, well, I have personally found nylon 12 to be especially strong in the Z-axis. It doesn't seem to break along the layer lines like most other materials do. Now, if you're looking at the spec sheet right now, you will notice that that spec sheet doesn't really corroborate that claim. And I haven't really done any rigorous tests to confirm it, but I still think it's worth mentioning. Polycarbonate. Now, this is better known by the SABIC trade name Lexan, and it's basically repeating long chains of this basic carbonate molecule over there, and those tangle up when it hardens, like other amorphous polymers do. It's naturally a transparent resin, though Stratasys only sells it in an opaque white color. Now, PC is way more impact resistant than ABS, as long as parts are undamaged. So I'll explain a little bit what I mean. If you're looking at the material spec sheet, this will make a little bit more sense. So Stratasys measures impact resistance in two ways. They're both called IZOD tests. There's an unnotched test where a test part basically just gets smacked by a hammer. And then there's a notched test where that happens, but beforehand, a little chip of the material is taken out, and then it's smacked with a hammer. So in polycarbonate, cracks propagate very easily. So once you've established that little crack propagation nick in the side of it, it doesn't do any better than ABS or ASA in those notched IZOD impact tests. Printing with PC. You can print with 7 thou, 10, and 13 thou layers. If you have a Fortis 900, you can go all the way down to 5 thou. Polycarbonate can print either with soluble support or with breakaway PC support. And although it might be tempting to always use soluble support, we kind of do here, PC support is cheaper, and it's easier to remove by hand than that soluble support is. And that is kind of important because the soluble support tank can actually cause some problems with polycarbonate. First of all, PC is susceptible to thermal shock. So it's a bad idea to take a hot part right out of the build oven and then toss it right into a cold bath, or even vice versa, a cold part into a hot bath. It'll probably crack. Now also, sodium hydroxide, the main component of waterworks that you use to dissolve soluble support material, that affects the performance of polycarbonate. So you should really try to keep soak times to 4 hours or less. Definitely don't leave it overnight. I've also personally found that polycarbonate tends to under-extrude whenever it starts the build, the contours, perimeter contours. And so I find that it's worth the time to open the file in Insight and add an extra contour. And I always check the box to link contours. And I find that helps to improve the appearance of those seams. Polycarbonate has a better tensile strength than ABS, but it takes almost twice as much load for it to break. So that means polycarbonate has a pretty high deflection. So it bends before it breaks. Just bear in mind that when it does break, it snaps. It doesn't smush or neck like ABS or nylon. It also has really high compressive strength, 5 tons per cubic inch before it yields, 14 tons before it breaks. So it is an excellent choice for low volume metal forming. And that's an application that most folks aren't aware of. You can use hydroforming, which is the application in this part on the screen, or even smash tooling. You'll get fewer parts before the tool breaks, but if all you need is a dozen or so, it doesn't always make sense to machine it out of steel. 280 degrees Fahrenheit is about as hot as you want to get with polycarbonate while it is under any sort of load. But that is pretty warm. That's 70 degrees hotter than ABS or ASA. And so that makes this a really good option for thermoform tooling, vacuum form tooling, that sort of thing. And although I personally don't have any direct experience annealing it, I understand that this can dramatically improve the bond strength between those layers because normally the impact strength in the z-axis, which is where parts are normally the weakest, is no better for polycarbonate than it is in ABS or ASA, unless you anneal it. It'll also raise the working temperature, the heat deflection temperatures, and the overall strength of the part. It basically makes it more like sheet polycarbonate, like you might be used to, the same material as DVDs and CDs. Those things are impossible to break. Like I mentioned with PLA, annealing is basically just you raise it up to near the glass transition temperature and keep it there for several hours and then take it slowly down. Also, polycarbonate is available in a biocompatible ISO certified blend. That's the ISO 10993 USP Class 6 certification. Moving on, PC-ABS. So this will be quick. This is an alloy of ABS and polycarbonate. It brings to the table the best of both worlds. So it's stronger by a third than ABS, and it's about twice as big. It's not quite as but it has resistance, so it does about twice as well in notch test. So once it's been damaged, tends not to crack worse. It is also not able to like carbon, and you can free to that all night. Also, it's half. So 370, and you're a nice space. And the F70 is the only machine to offer this material in white. Otherwise, it's only black. So I would suggest using PC-ABS for anything you would normally use ABS for, but which maybe needs to carry more of a load, or something that might be subject to bumps or some light abuse. Impacts, sort of drop proof. It really is a great low-cost choice for assembly fixtures, for nests, especially those that need to cradle finished parts, because it's non-marring. And if you need a smooth surface, acetone will dissolve it just like ABS or ASA. All right, I'm running a little bit behind, so let me quickly check. Let's see, we already covered nylon 6. I'm sorry, nylon 12. There we go. All right, let me double check that there are any questions here. Looks like y'all are saving them for the end. That's fine. Okay, when you have an application with very specific needs, that's when you're reaching for high performance materials. Now, most of these are high heat materials, and so that means that they might require a mechanical upgrade to your machine, depending on how you bought it, to allow the chamber, frankly, to get hot enough, and in some cases to allow the components to last. I'm going to try and get through this pretty quickly so I can get to questions. All right, I'll start with nylon 12 CF. This is the same nylon 12 that we just discussed. So that's the polyamide with 12 carbons in that atom, in that molecule. But this is loaded to 35% with carbon fiber, and that's a pretty high fill, and it has especially long fibers, 150 microns. This stuff is stiff, really stiff. It's also very abrasive. It needs hardened drive components and a hardened or abrasion-resistant filament path. So there is a mechanical upgrade involved in order to run it, and that includes a dedicated head. So before you run nylon 12 CF in practice, you need to unload the model material and the support material, power the machine down. You're going to unfasten the head just like a tip change, but then you also unscrew the power cable, disconnect the filament tubes, and remove the head. It doesn't take long, 2-3 minutes. And you put the new carbon fiber head in and reverse that process. Switching the heads around maybe takes 5 minutes, but all told, it takes about a couple hours to, after you replace the head, wait for things to heat up and run through some calibration. It's that shutdown process that slows things a bit. Now, while you're actually working with Nylon 12 CF as a machine operator, you should wear gloves. Although the sacrificial tower, which is mandatory, it does do a good job of catching drool, but whatever little chunks do end up on the part, they're quite sharp. And trust me, you don't want carbon fiber splinters. So I would also suggest knocking those off with a deburring tool. If you are processing your parts in Insight rather than GrabCAD Print, I would suggest adding a slight negative spacing between contours and rasters. Now, your results may vary when you actually print, but I've found that sometimes we get a little bit of under extrusion, especially on the bottom-facing layers. And that's especially likely to happen if your tips have a lot of hours on them. This stuff eats through tips. So, yeah. Right, so as far as applications, did I mention that this stuff is stiff? It has, let's see, twice the flexural strength of Nylon 12, but the stiffness is, so it's an order of magnitude higher. Nylon 12 CF does build solid by default, like if you use GrabCAD Print, but I think that its greatest strength is when you, pardon the pun, is when you print it with a sparse infill, honeycomb infill. You basically get a very, very strong but very lightweight part. So this material also post-processes very well. So if you have access to a media blast cabinet or a mobile polisher, that will give this a as might happen with ABS and some of the less durable materials. Okay, let's get into the Ultems. Ultem 9085. I got my notes out of order here. Okay, so this is categorized as a polyetheramide. Savic makes, they're also PEI is the acronym for polyetheramide. So these materials are extremely high strength, high heat, and chemical resistant. Like nylons, from a chemical perspective, you basically have a repeating pattern of this specific molecular chain. That chain, you notice all those hexagons there, it has a lot of what are called benzene rings. They're very chemically resistant and heat resistant. So unlike nylon there. Now, when you actually build with nylon, it's going to take a while to load the material. The actual loading process doesn't take any time at all, but there's what's called a heat soak time. So about 4.5 hours to bring the oven temperature up to temperature, and that also accounts for the time it takes all the metal components to absorb that heat. That way, all of your parts, all the parts of the machine and the control system have all expanded at the same rate. So it helps to eliminate any slop, to make sure that you're getting material properties that you were promised, or accuracy, excuse me, plus or minus 0.005 of an inch. And the reason is that you're bringing this oven up to about 400 degrees Fahrenheit, and that takes a while on its own. Now, Ultem 9085 comes in both black and a natural color, which I have here on the screen. If you are building with that material, it looks really similar to the support material. So when you build your calibration patterns, I would recommend scribbling over those lines with a Sharpie. It helps to add contrast. And do use your little magnifying glass that came with the machine, the jeweler's loop, because calibration is the key to getting the support off of Ultem. Whether it be Ultem 9085 or Ultem 1010, if it's calibrated and dialed in, it'll be easy to get that material off. So last thing, I'm running out of time here. I should also mention that Ultem 9085 is certified for end-use aerospace parts, and it's also it's been tested for fungal resistance. And if you're one of the few who has the H2000, otherwise known as the infinite build machine, this is the only machine only material that runs on it. All right, Ultem 1010. I just got 2 more materials left here. Ultem 1010, basically the same thing. The same tips and tricks go as with 9085. Ultem 1010 is able to build at 20 thousandths of an inch on the Fortis 900 with the T, I think it's called T40 tip. So it takes a long time to load. It's very important that you calibrate well, spend extra time calibrating. And with Ultem 9085 or 1010 or Antero 800 NA that we're about to talk about, you're going to remove support while it's hot. Not so important with Antero, but you've got about 5 minutes after the part comes out of the oven to easily remove support material. If it gets hard to remove and you start being tempted to break out the chisels, put it back in the oven. It'll remove easier after it's been in there for another few minutes. Now, with Ultem, technically every time you heat cycle that bond between the model material and support material becomes stronger. You are essentially annealing that chemical bond. So you're going to want to act fast, because after, say, 6 or we'll call it a half a dozen cycles through the oven, depending on the size of the part, it'll become very difficult to remove that support material. So you're going to use Ultem for tooling applications, especially very high heat, high strength, and for end-use parts that can't otherwise be practically produced using traditional means. Because potentially extremely high heat, volt, or smoke toxic, you can use this for underhood automotive applications like exhaust manifolds, that sort of thing. I should also mention that there's a certified grade of Ultem available that includes material tracking information, sourcing information. All right, finally, Antero 800 NA is a new thermoplastics from Stratasys. It's a semi-crystalline thermoplastic, sort of like nylon is. Since it prints so hot, it sort of feels as it's printing, and that allows it to be especially strong. This is a PEKK material. That's a polyether ketone. Many of you are familiar with PEKK, polyether ether ketone. A little bit different, not quite the same heat resistance as PEKK, but much better chemical resistance. Notice again those benzene rings, those hexagons in the molecular structure. Just like with Ultem, your calibration is key to being able to remove support material. Unlike Ultem, this support material is actually quite easy to remove after the part has cooled. So that'll save you a little bit of time and frustration trying to remove supports with gloves on. Just like Ultem, it does need to be printed hot, so it will take quite a while to load. I have found, although we just got our Antero and we've only printed a few jobs with it, it prints like a dream. The parts really look good and clean, no wispiness along the corners. Layer lines are, the seam lines are well controlled. It is a really nice material. It's expensive, but if you're using PEKK, it's because it's the only material that'll do what you need to. And that's really why Stratasys developed this material. Antero 800 NA refers to the fact that it's got nothing else in it. But coming down the pipe, there will be other materials, or other types of Antero, which include maybe fiber fill or ESD 7 or ESD certifications. So you're going to use this again for tooling, high heat, high strength end-use parts, but especially for chemical resistance. This material carries that mill standard 810G for chemical resistance. And again, I mentioned that this was specifically developed, maybe I did, it was specifically developed for aerospace applications for use under the airplane, where it would be in contact with antifreeze and oils and all the sorts of things that, again, normally chew up other parts. So, okay, I know I went over a little bit, but I'm calling time.